Hi, myself Jawaharlal, lecturer in electrical engineering. Today I am going to discuss about the ideal transfer. Please subscribe my channel for the next video on this topic and also in the field of electrical engineering. If you don't subscribe, then the video will not come at your end. So please subscribe my channel. Now, for ideal transformer, winding resistance are negligible. So winding resistances are negligible, then the copper losses also negligible, and hence it is assumed to be zero. Second is there is no leakage flux, that is the same flux links both the windings. The iron losses, it means the eddy current loss and hysteresis losses in the core are negligible. The core has infinite permeability, so that negligible MMF is required to establish the flux in the core. So these are the requirements for a transformer to be an ideal. In the next slide, we will see about the uh, ideal transformer on no load. The ideal transformer may be on load, may be on no load. So in this slide, I am giving you the ideal transformer on no load. Here you see the figure. So this is the ideal transformer on load. So consider an ideal transformer on no load. Secondary is open circuited at no load condition. Under such condition, the primary is simply a coil of pure inductance. So when an alternating voltage V1 is applied to the primary, it draws a small magnetic current Im, which lags behind the applied voltage by 90 degrees. You see here, there is a Im and this is a V1 applied voltage. So it lags behind the applied voltage by 90 degrees. And the Im magnetizing current and flux are in phase. So this alternating current Im produces an alternating flux phi, which is proportional to and in phase with it. You see in the phasor diagram. The alternating flux phi links both the windings and induces EMF E1 and E2, E1 in the primary winding and E2 in the secondary winding. The primary EMF E1 is at every instant equal to and in opposite to V1 by applying the Lenz law. Both EMFs E1 and E2 lags behind flux by 90 degrees. However, their magnitude depend upon the number of primary and secondary turns. Here you see the E1 and E2. Both are lagging to flux phi. Now, figure 2 shows the phasor diagram of an ideal transformer on no load. Since flux phi is common to both the windings, it has been taken as the reference phasor. I have shown the primary EMF E1 and the secondary EMF E2 lags behind flux phi by 90 degrees. Note that E1 and E2 are in phase, but E1 is equal to V1 and 1 out 80 degrees out of phase with it. For an ideal transformer, because there is no losses, so these E1 and E2 are equal, but they are out of phase by 180 degree. That means E1 lags V1 by 180 degree. Here, due to the ideal transformer, E1, E2 is also equal to the V2, but it is in phase with the V2. So this is a phasor diagram of the ideal transformer, and this is the block diagram of the or schematic diagram of the ideal transformer on no load. Thank you.